Did you hear that? No? If we were inside a whispering gallery shaped like an ellipse, you would have.
Welcome everyone! Today, we'll be solving a math problem about architecture, sound, and the power of ellipses. In some famous museums, there's a special room called a whispering gallery. Usually, the floor is shaped like an ellipse.
If one person whispers at this focal point,
the sound bounces perfectly and reaches the other person across the room. Now, let's move on to our problem. A museum's whispering gallery has a floor shaped like an ellipse. Two people stand at the foci 30 meters apart. The horizontal major axis of the ellipse is 40 meters. If a whisper from one focus can be heard clearly at the other, what is the length of the minor axis of the room? So the given values are the distance between the foci, which is 30 meters, and the length of the major axis, which is 40 meters. These two values are also equivalent to 2 times c and 2 times a. As we all know, for every ellipse, there is a special relationship between a, b, and c, where a represents half the major axis and b represents half the minor axis, and c is the distance from the center to a focus. If we substitute our values to the formula, this is what it looks like. 2c, or 30, divided by 2 is 15. 2a, or 40, divided by 2 is 20. 15 squared is 225, and 20 squared is 400. Transpose negative b squared as well as positive 225. 400 minus 225 is 175. Since b is squared, we have to get both b and 175's square roots. The square root of b squared is b, and the square root of 175 is approximately 13.23. But since the formula for a minor axis is 2 times b, our final answer would be 26.46 meters. So the minor axis of the whispering gallery is approximately 26.5 meters. That's the width of the room and the elliptical shape that allows even the softest whisper to travel across. All this solving has got me thinking, why don't we solve for all the parts of this elliptical room? So here's what we already know. A is equal to 20, and B is equal to 13.23, C is equal to 15, and center is at 0, 0, or at the origin, and the major axis is horizontal, which means that the major axis is the x-axis. Since our major axis is the x-axis, this is the set of formulas we'll be following. From the table, we already know that the standard equation of our ellipse would be x squared over a squared plus y squared over b squared equals 1. We also learned from our previous problem solving that a squared for this particular problem is equal to 400 and b squared is equal to 175. Since the major axis and center were already given, let's go straight to vertices. The formula is pretty easy. Since the center is at the origin, the value of x for the ordered pair would be positive and negative 8, which is 20, and 0 for the value of y, thus the major axis is along the x-axis. Co-vertices is similar, but switched. 0 would be the value of x, and as for the value of the y-coordinate, that would be positive and negative b, which is 13.23. By now, you may notice an alternate thing going on, because in the foci, 0 is placed again as the y-coordinate, with positive and negative c, or 15, as the x-coordinate. We have 4 answers for the endpoints of the lattice rectum, but we only need one important formula, which is b squared over a. First, copy positive and negative c from the foci and replace 0 with the value of positive and negative b squared over a. b squared over a, or 175 over 20, is 8.75. Make sure that there are no ordered pairs with the same x and y coordinates, or simply that there are no repeating ordered pairs. As you may notice, the answer for the directrices is not in an ordered pair form, but rather written as an equation. This is because the directrices are lines. Again, since our major axis is the x-axis, the formula is x equals positive and negative a squared over c. Substitute the given into the formula and we get 400 over 15, which can be simplified into 26.7. Eccentricity's formula is c over a, which is also 15 over 20, or 0.75. One characteristic about an ellipse is that its eccentricity is always less than 1. Next, we have the length of the latus rectum, which is simply 2 times b squared over a. Just take the value of b squared over a we got earlier, which is 8.75, and multiply it by 2. You'll get 17.5. We can get the length of the major axis basically by multiplying a by 2, which is 40. The length of the minor axis is solved similarly, but multiply 2 by the value of b, which gives us 26.5. Finally, this is what the points and lines look like when plotted in a graph. And this is what our elliptical Whispering Gallery's floor plan looks like from above.